Hello and welcome to this Diabatix webinar, Electronics Cooling Taking Air Cooling to the Next Level. I'm Reshmaa Selvakumar and I will be your host for today. I'm an application engineer at Diabatix and I'm the interface between our clients and the software. I help with providing engineering support, training, and getting them started on the platform. In terms of a background, I have a background in computational mechanics and aeronautical engineering. In today's workshop, we will focus on a forced convection heatsink for electronics. If you have any questions, please feel free to ask them on the chat box below, and I will answer them towards the end of this session. To give you a brief summary of what we will see in this webinar today, it will be setting up a case on the platform. We will look at library parameters and how to set or define our own library parameters in different categories. Then we will look at the post-processing of this case, and after that I will answer your questions before concluding this session. Now, without further ado, let's take a look at the case that we will be discussing in detail during this webinar. In this case, we will focus on cooling the electronics with forced air cooling, that is, using fans to push the air to further cool the electronics that are mounted on it. Let's take a look at the assembly. This is the geometry of the heatsink that we have today. You have an interface over here. You have two centrifugal fans on this heatsink. And underneath this is where we have some PCBs that are mounted onto the heatsink that need to be cooled. The area over here is where we expect to design or create cooling channels for the fluid to flow. So this is our expected fluid region where the fans will push the air to further cool the electronics. To simplify the case on the platform, I have removed the fans and the interface from this assembly. So what you see here is the plain solid region or empty geometry, as we like to call it, without all the excessive details that can be further modeled as boundary conditions. So if you look at this empty geometry or your solid region, it uses an aluminium alloy, which is an yield with a conductivity of 180 watt per meter Kelvin. The other material properties include the density, which is about 2,700 kgs per meter cube, and also the specific heat, which is around 896 joules per kilogram Kelvin. So now that we have all the material properties that are involved in the solid region, let's look at the next thing, which is the fluid region. So, like I mentioned previously, the fluid region is basically where the fans that are situated on top will push the air towards to cool the heated PCBs or electronics. Now, in this case, the fluid that we will be using is air, of course, the density of which is about 1.204 grams per meter cube, and the conductivity is around 0.02514 watt per meter Kelvin. At the inlet, there are two inlets for two of the fans that we've seen previously, and the fan type or the centrifugal fans that we will be using are by Sunon with the dimensions of 50 into 50 into 15. And I will show you how to model these inlets using fan curves. The temperature at the inlet is around 293 Kelvin, which is the same, which also influences the air properties that I have mentioned over here. The outlet itself will be at this end, and it's just a normal pressure outlet that we will be modeling. Now, let's take a look at the boundary conditions or of the heat generated by the different electronics that are mounted. So, like I mentioned previously, these PCBs are mounted underneath at the bottom of the heatsink, and instead of including them as individual pieces, we will be including them as boundary conditions or boundary types. So I have 4 PCBs that are mounted on this heatsink, one large PCB with a heating power of around 72 watts, and 3 smaller PCBs with a heating power of around 36 watts. The next thing that we have here is the design specifications and the design space. The design space, if you take a close look, is very similar or very much in the region of the fluid region. It's a sub-region or a sub-part of the fluid region. You see here that the manufacturing constraints involved with the design space is that it's going to be die casted with a minimum fin thickness of around 10 millimeter or 0.01 meter. I will also walk you through the process of including these manufacturing constraints on our libraries, and I will show you how to model them as well. The optimization target that we're looking for is to minimize temperature on all the PCBs. This design space is where we will have the software create all the cooling channels for the air to flow. Now that we've looked at all the 3 different regions and the heated and the boundaries, let's take a look at the workflow for this webinar. I'm going to start with doing the case setup on the platform. I'll walk you through the entire process. After that, we will look at some of the parameters that I will use in the case setup, like the fan curve and the manufacturing settings, and I will walk you through how to include them in the library. I will show you also where to look for these parameters in the libraries and also how to include them on our libraries page. After finishing this, we will look at how the post-processing looks on the platform itself. Let's get started. All right, when we first log into the platform, this is the first page that you'll land on, which is the projects page. We understand that everybody has multiple projects that they work on, along with each project having different cases. So we offer the same kind of management by the platform itself. So as you can see here, you can see different projects, and also the status bar indicates the status of the project. So the orange yellow color refers to a case that has just been created. The blue refers to a case that is running on the supercomputer currently, and the green refers to a case that has been finished or completed. So it's very simple to add a project and to begin our case as well. I'll show you how to start from adding a project to finishing the case setup and for the post-processing. So let's just start with adding the project. Let's give it a name, say forced air cooled heatsink. We can give it a description. I'm going to say fan cooled die casted heatsink for electronics cooling, and then I add the project. So once a project is being added, you can then create your individual cases inside the project. So we begin with adding a case, giving a case a name. So let's say, since it's a design case and we want to focus on temperature minimization, let's just call it temperature minimization design. The next thing that you will have to do is choose a case type. And there are 2 different case types available. One is a design case and the other is a simulation case. A design case is really your optimization case. It's when you want the software to design the cooling channels and the pins and the fins for you in the heatsink, whereas a simulation case is really just your CFD simulation. So now what we are going to do is a design case. So let's just choose design and add case. So the first step that we have to do now is to start the setup. And for a case setup, there are 5 major things that we have to cover. First being including the geometry. And for that, we'll have to upload a step file from our relevant CAD software that we use. So we just select a step file and we populate the case. So what happens when we upload the step file from our CAD environment is basically the platform reads the relevant regions and boundaries and subregions that we have defined onto the platform directly. So as you can see, there are already all the regions, boundaries, and subregions that I've defined in my CAD environment that is already on the platform. So from here, our next step is to add the boundary conditions. So before that, I just want to show you the different regions that I have here. Let's start with region 0. So region 0 over here is basically my heatsink, and we've seen this in my presentation as well. So this is the outer layer and this is the heatsink, and below over here is where I'm going to expect for my PCB or my electronics to be mounted on this heatsink. So you can also see that as boundaries that I have defined. So this is where exactly my PCBs are going to be mounted around those bolts and nuts that you see over here. Let's start with setting up this region first. So you just click on region 0, choose the region type. So in this case, it's a solid. So I will choose solid, and then I can give it a name. I'm going to call it heatsink. The next thing I can do is I can select the relevant solid material for it from our solid library. So I click select material. I'm going to go with an aluminum alloy. Let's say it's 6061 annealed. So I'm going to go with that. So there are no other properties, physical properties that need to be included for this region. So my boundary conditions for this particular region is done. So now I can look at the individual boundaries on this region. So let's start with boundary 0 again. This is going to be my large PCB. I can also visualize it for you. This is going to be my large PCB that I have, the one big source of heat on this heatsink. So this is going to be a heated wall boundary type. So I will just go with that. I will call it PCB1. And the heating power for this is around 72 watts. And that's what I'm including over here. Now let's look at the next boundary, which are basically the 3 smaller PCBs that are mounted. So we can set this up very quickly. We'll start with boundary 1, choose heated wall, call it PCB2. And the physical property, so the heating power for each of these small PCBs is 36 watts. So that's what I'm going to go for. All of them are pretty equal. All of them are equal, so that's what I'm also giving as the heating power, 36. And then heated wall again. Let's give it a name, PCB4, and a heating power of 36 watts. Now, as you can see here, I have finished setting up the boundary conditions for this particular region. And as I finish setting it up, there are green check marks that denote the fact that this region and boundary has finished being set up from our side. So all you have left to do next is the next region. So let's take a look at that. This is my fluid region. This is my fluid region, as you can see. So this is where I expect my fluid to flow. So this would be where your fan inlets are, and this would be where the outlet is. And the fluid, which is air, will be pushed along this region. So let's start setting this region up. We start with region 1, choose region type as fluid, give it a name. Let's just call it fluid again. and then select the relevant fluid material. In this case, I'm going to go with air at 293 Kelvin because that's my inlet temperature. So I'm going to go with the exact properties at that particular inlet temperature. In terms of the turbulence model, I'm going to go with K omega SST. And there are no other properties that I need to include for this region. So let's move on to the next boundary. So to visualize the boundary itself, like I mentioned, this is my fan inlet and this would be my outlet. And this subregion is where I would want the design to be constructed or created. So let's start with the boundaries. Boundary 0, that's my pressure outlet boundary. So I'm just going to call it outlet. So this is just a constant pressure outlet. I don't have a particular pressure value that it needs to maintain. So I'm just going to have it as pressure outlet, give it a name and leave it as it is. The next two boundaries over here are my fan inlets. So I will choose fan inlet in the boundary settings and let's call it fan 1. The inlet temperature, like I mentioned, was 293 Kelvin. That's what we used for our air as well. And that's what we will include here. And now we will also select the fan or the fan curve or the fan parameters that are relevant for this case. So you just click on select fan. And from our libraries, I will be choosing the fan that's relevant or is close to the dimensions that I have over here. So I repeat the same for the second fan inlet. So the inlet temperature remains the same, 293 Kelvin, and the fan that we're using also remains the same. So I'm just going to find the one that's relevant to the dimensions that I have and select the particular fan curve. Now, as you can see, this region is also almost finished. The only thing left is your subregion. So now we finished two steps. One is including the geometry on the platform. The next is including all the boundary conditions that are relevant for the different regions we have. The third step is including a design region and also at the same time including manufacturing constraints. So in this particular case, this would be my design region. It's a part of the fluid region, and on the heatsink itself, if you have to take a look at it, this is where it will be, and this is where I want my channels to be created by the platform. So the design region is important because this is where you will include your manufacturing constraints and your manufacturing type. So let's just name this region as design as well. We'll select a material. I'm going to use the same material that we used for my solid region, which was an aluminium alloy. And now comes the most important step, which is to include your manufacturing constraints. So we start with including a manufacturing type. In this case, it's die casting. That's our focus. So we're going to go with die casting. And then we choose the relevant manufacturing settings. Now, the manufacturing settings are very important because this is what gives the software the information about the minimum feature size, the angle, the bending radii, and so on. So it really tries to meet all these constraints of drawing channels that can still be manufactured with the manufacturing settings that you are looking for. So it's very important to give the right manufacturing settings to have the right level of manufacturability of the completed design. So at this point, we've finished all the different steps. The only thing left to do is to include our optimization targets and our optimization constraints, if any. So just as a recap, we've included the geometry on the platform. After that, we've included the boundary conditions of these different regions. The next thing we have done is to include the design region, after which, while setting up the design region, you include your manufacturing constraints. And the last thing that you do is you include your optimization targets. So like I mentioned at the start, What we are looking to do for this case is minimize the temperature on all the heat sources. So what we do is we first click on one of the heat source, let's say PCB1. All the way below, we have the option of add target, and then we will choose our optimization target, which is temperature minimization. So that's automatically included with a specific weighting factor. So the weight of the target is also included, and it's generally between 0 and 1. You can read more about it when you hover the I value over here right next to it. It's basically the weight of the target function, and it can be changed when you have multiple targets, or you want to say, especially when you have multiple targets, you want to say this target is more important for me as opposed to my second target or my third target, and the value always has to be between 0 and 1. In our case, all of our targets for the 4 PCBs are equal, so I'm not going to make a change. Let's repeat the same in the next PCB as well, our target being temperature minimization, and then we include it in all the 4 PCBs boundaries that we have over here. And that's it. I don't have any other optimization constraints to include. So I have basically completed setting up the case. I've included the geometry, the boundary conditions, the design region, the manufacturing constraints, and also my optimization target. So at this point, what I do is I will validate the geometry just to ensure that there's no overlap in the regions and there's no any issues in terms of the geometry itself. And then I will submit the case. Now, when you submit the case, it consumes a certain amount of credits, which is basically the computational resources that are needed to run this case. And you have two options. So you can run either a detailed design case or a conceptual design case. A detailed design case is really a high resolution, accurate, optimized design that is manufacturable. So it's really when you start and finish the optimization, you end up with a case that is ready for manufacturability, and it's an optimized design that meets all your constraints and your targets. Your conceptual design case, on the other hand, is more of a first estimation of what you're looking to achieve. This is really good to use when you're not sure of your parameters, or if you want to optimize for different positions of inlet and outlet. So you can run a few conceptual cases, take a look at how the design looks and how that affects the design, and based on that you can fix your parameters or change them according to that before you run a detailed case. So for now, I'm just going to start a detailed case with 100 credits. I also would like to mention that over here, my 100 credits are not burnable credits, but rather credits that will be in use while this case is running on the supercomputer. So once the case is finished, I will have these 100 credits back in my wallet, and that's how the credit system works. I'm just going to give OK now, and your case is being submitted and is running on the supercomputer. On a side note, before I get started on the next thing, I do want to mention that the reason that we have not included a pressure drop constraint in this case setup is simply because it's not necessary. We're using a fan curve as an inlet, and because of that, the fan performance curve kind of takes the pressure drop constraint into account. So we don't have to include that. All right, now that we finished the case setup, the next thing that we're going to look at is the library parameters. I'm going to focus on showing you the parameters that I have used during this case setup, specifically the fans, the fan curves, and the manufacturing settings. So that's what we're going to be looking at right now on the libraries page of the platform. So let's start with perhaps the fans first. And this is an example of a fan curve, and a fan curve itself is just basically a group of points that represent the relation of the quantity of the fluid passing through the fan relative to the pressure drop. And we will be modeling this on the platform. So let's take a look at, let's go back to the platform. So this is the libraries page of the platform. And as you see here in the libraries page, there are different categories of parameters that are available. So you have the materials category, under which you can have access to solid materials, fluid materials, and also thermal interface materials. So it's very simple. You can find an extensive library already available, and of course you can also define your own solids or fluids or thermal interface materials. The second category is the fans and the pumps, and the third category is the manufacturing types. So we're going to work on the fans first. So today, in my case, I used a fan. I'm just going to tell you how to include your own fan and also define your own fan curves. So you start with adding the fan. We give it a name. So I'm just going to give the dimensions of the fan that I used as a name, or I can just say fan along with those dimensions. You can give it a description if you want as well. The next thing you would include is the speed, the volumetric flow rate, and the pressure. Now, these are all parameters that you can find with your fan manufacturer. So you can ask them if you want to know the correct details of the fan that you're going to be using. So the speed of this fan is around 5,000 RPM. The flow rate itself is, it needs to be in cubic meters per second. So that's around 1887. The pressure in Pascal is 166.72. Next thing that we're going to do is include the different points of the fan curve. So like I said a little before, the fan curve itself is just a representation of a group of points that kind of give you a relationship between the pressure drop and the amount of quantity of fluid that is passing through the fan. So what we have here is the total pressure versus the volumetric flow rate. They usually have it in different units from your fan manufacturer. It's also common to have them as CFM or cubic feet per minute, and then there's also the possibility of having inch H2O as a unit as well. It's very simple to convert them to Pascal and cubic meter per second, and to add the different points. Let's start with at zero, when the when the volumetric flow rate is zero, and the total pressure at that point is around 169.212 for this case. The second point that we'll have to add is around 0.00004, and then the total pressure there is 129.45. So as you add the points, the curve itself begins to build on the platform. So we can just keep adding a few more points. I'm going to do 3 more points to give you an idea of how it looks, so you can also include it when you try and recreate this case on the platform as well. That's wrong. It's 92.28 at point. The next point is around 0.08. The total pressure is around 74.93. And this is going to be my last point, and the total pressure is around 25.54. So as you add points, you can see that the fan curve just built itself. It's just the total pressure in relation to the volumetric flow rate, and this is what I have used in my case setup today as well. This is the values, and all you have to do is check with your to include your own fan, you just have to check with your fan manufacturer and get the relevant details like the pressure and the volumetric flow rate from them, and just include it on the platform. So that's it. We've included all the basic parameters along with the different points for the fan curve. We just add fan, and now our fan is available on the library for you to use. So now that we've finished including the fan parameters, let's look at the manufacturing settings and the manufacturing types. So in this case, we use die casting. So the manufacturing settings that are relevant to this um, manufacturing type is seen on this picture here. So we'll start with this part, which is basically the fin thickness. So you'll have to include a minimum fin thickness as well as a maximum fin thickness. The next thing to include would be the bending radii. So what you see over here is the inner bending radii, um, which is at this point, and over here is the outer bending radii for each of your fins or channels. Um, so once you've included that, the next thing is the angle, and this is just the draft angle of the fins that you will have to include, and then of course the delta, which is basically the depth of the cooling channels. So other than this, the only other parameter that you need to include is the orientation, which is basically the orientation of the demolding direction um, for when you die cast it. So these are the parameters that you'll have to include. So let's just take a look at the libraries page again. All right, on the libraries page now, because we're including manufacturing parameters, we'll have to include them in manufacturing settings. You click on add manufacturing, give the manufacturing settings a name. I'm just going to call it die casting for forced cooling heatsink. You can of course give it some other description if you want, and then you choose the manufacturing type. So like I mentioned before, the manufacturing type over here was die casting, and as you see immediately once you choose the manufacturing type, the relevant parameters that are needed already pops up. So I'm going to include the exact values that have been used for the case that I showed you earlier. So the RF min is around 0.01, so it's about 10 mm. So the feature sizes you have to include in meters, so be very careful when you're including these parameters to ensure that they're in the right units. The max value is around 0.02. The inner bending radius is around 0.001, and the outer bending radius is around 0.002. The angle, the draft angle is 20 degrees, and the depth is 0.001, and the demolding direction, so the orientation of that was along the y-axis. So we've included all the parameters that I've used for my manufacturing settings today in this case, and then you just simply click add manufacturing, and now this will be available in the library for you to use. Again, in this case as well, reach out to your manufacturer to understand what manufacturing settings work for you when you create your own case, because each case is different, and each case's manufacturing technique and manufacturer can be different as well. So do check with them with what the relevant sizes, feature sizes are to include for your case. Now that we've finished including the library parameters, let's take a look at the workflow again. So now we finished the case setup, after which we took a look at all the library parameters. I also showed you how to include your own library parameters, and now we can look at the post-processing. So when we submitted the case, during the case setup, you would have noticed that it takes about 2 to 4 weeks for a finished design. And I've taken the liberty to already run the same case earlier this month. I already set up the case and I have the results. So the first page that you see when you open a finished case is this page, which is basically your case summary. What you see here is all the important values or parameters that you have to take a look at that is relevant to this case. So you can already see like the temperature in the different PCBs, temperature at the inlet and the outlet. You can also take a look at the pressure, the mass flow rate, and you'll also see some of the, of course, the input data that you give, like the heating power, for example, and so on. So you have all of these important values as a complete overview on this page for you to take a look at. A cool feature is that you can also change the units of these parameters or values, and you can see them in the units that you're most comfortable with. So this applies to all of the different parameters that you see here, and you also have the option to um, change the units. The other thing that you can do on this page is that you can download the results and you can download the design. The design, when you download, would still be a step file that you can download, and you will also have all of this information when you download your results. The next thing is the view setup option. So when you use this, you will be taken back to your case setup and you'll be able to see the case setup for this case. If you want to run the same case but with slight changes in the parameters, so say for example, you want to run the exact same case, but you want to change like the heating power, then what you can do is instead of having to start from scratch, you can simply duplicate the case, change the parameter that you want to change, and submit the design. So that is also a possibility with the duplicate option. You make a copy of the same case in the same project, and you can uh, uh, try another parameter or run the exact same case and take a look at it. In the case 3D results tab, what you can see is basically your design, your finished design, and you'll also be able to see your results. You basically can visualize your results on the 3D model or on the 3D model. So you'll be able to visualize all of them. Again, you can do this for all the regions and all the boundaries that you had included in your case setup, and you will also be able to take a look at them individually and color them individually in this tab. So say for example you want to look at the design and you also want to look along with the surface plot of the design, you also want to look at the streamlines or something, you can take a look at it via this tab. So let's take a look at this. I can already see some features over here. I'm just going to move it. I'm going to in in a nice position for us to visualize it. Well, okay, the first thing that any of us want to see is, of course, indeed the design. And I'm just going to hide everything else so we can visualize the design. The outlet, and this is how the design looks. So just to recap, I'm sure you remember, but this is where the fans are. So that's our inlet, and this is the outlet, and this is how the design looks. uh, the finished or completed design looks from the software. You can also color it in a different color if you want to take a better, maybe this one. It looks, you can take a, you can have a good look at the different fins or features that have been created by the optimized software. Um, we'll also Another interesting thing to do would be, of course, to look at the surface plot itself, but with relevance to say the temperature or an actual parameter. So what you can do then is, instead of coloring it by a solid color, you just click here and then you can take a look at it from, say, the temperature perspective. Just and then you can take a look at it. So of course, you have to set the right range over here to really visualize it in a better form, and you can set it up that way. What is also interesting for me is to take a look at the the streamlines. So we should probably also take a look at that. So these are your streamlines. I'm just going to color it with say your velocity, and this is how your streamlines. I'm just going to move it so out so we can visualize this properly. So this is how the streamlines look, and that's something that we can already see on the platform. So you can look at the surface plot for different regions and for the different boundaries here on the platform itself. You can really explore the different options, the different parameters that you can see, and so on and so forth. So you can really um, explore and uh, assimilate or familiarize yourself with the platform's post processing as well. Another really cool feature for me is being able to take a screenshot. So, say this is a picture that I'd really like to use in a report to share with my colleague or with someone from management. Then I just simply take a screenshot with a transparent background, give it, let's say, streamlines, and then I can simply download it as a PNG file that so that I can use it on my report as well. So this is the post-processing side and the results side of this case, and you can really take your time at looking at it. So I think with this we have essentially uh, completed everything that we had decided on for this webinar. So we finished the case setup. We also looked at the library parameters and the post processing of the results. And I think now is a good time to look at your questions. Now, as promised, I'm going to look at some of the questions that you've passed on to me. So I'm going to try and answer some of your questions. Um, the first one that I have here is, which web browsers are compatible with the platform? Most of the modern web browsers are compatible, so our platform works with any of them. So like Google Chrome, Safari, Firefox, Edge, all of them, you can use it. I also know that on Chrome and on Firefox also, I think you can download the plugin version, so you can access it directly, like a shortcut from your desktop without having to open the browser and look for the sign-in page every single time, and the rest of the procedure remains the same. It's just kind of like a shortcut to access it. Um, that's a possibility. So I'm going to look at the next question. Is it possible to import a mesh from another software? At the moment, it's not possible to import a mesh from a different software. It's also because we already offer you an automated meshing, which is built in, and it's designed to automatically create a mesh for your case, but that's relevant to your case and your constraints and things like that. So it's already automatic and it's also built in, so you don't quite have to worry about the meshing, and it's preset on the platform itself. Um, Next question. Most of the so this question is about looking at solutions in 3D. So there's it says that there seems to be a lot of 2D solutions. How about allowing for fully 3D geometry, for example, by which can be achieved, for example, by 3D printing? It is possible at like the case that we looked at today. The manufacturing type that I went for was die casting, which is why you have those kind of shapes and that kind of geometry. But you can use additive manufacturing or 3D printing and have more free form, cool, 3D shapes as well. I can also perhaps quickly pull up some pictures of it. So, for example, this one that I'm going to share my screen now again. So, for example, this one that you see on the website, this is more of a 3D shape for a natural convection case. So that is also possible with the software. It really depends on what kind of manufacturing that you're looking for, and that will influence the geometry of the design itself. So that's something you can look at on your own. All right. The next question. Can I run multiple simulations while I also have a design case? Yes, you can. You can run as many simulations or designs as you want. Your only limitation would be the number of credits that you have. So uh, the credits itself are not burnable, like I mentioned. So as long as you have a certain number of credits, or it's being you can run multiple simulations as long as it's not in use as well. So if your credits are in use, you might have to wait to regain those credits, but otherwise there's no issue in running multiple simulations. Maybe one more question before we finish up. What is the difference between a target objective and a constraint? How would you differentiate the two? Uh, okay, this is actually a good question. It's quite important as well to understand this. What we define in diabetics is targets, and there can be two types. One is an objective, and the other is a constraint. An objective is really what you're trying to achieve with the optimization or design case. So it's really what you set as your target to achieve. So it can be as minimum as possible or as maximum as possible. So something like temperature minimization is an objective, and something like maximize cooling efficiency would also be an objective. A constraint, on the other hand, is really what you're looking to satisfy, or your condition that needs to be met or satisfied. So, say for example, you have a maximum pressure loss, and you don't want your heat sink to exceed that pressure loss. Then what you would set up is a pressure loss constraint. It's the same procedure to add either. It's just you go and you add target, and you choose pressure loss, and you give the maximum value, or that would allow for your case. So that's how you'd set up a constraint, and that's what's different from an objective. There is also extensive documentation on this subject. You can find it on the website, um, and you can see the explanation of the different targets, and what an objective and a constraint means, so on and so forth. Um, I'm going to stop here because unfortunately we don't have a lot more time. But I do see there are lots more questions, and I will reach out to all of you directly to answer your questions. If you have any other questions, you would like to know more about the platform, you would like access to the platform, you can always reach out to us either on uh, either on phone or through the website or via email or LinkedIn. We will assist you in the best way possible. Thank you for joining me today. I really enjoyed it, and I hope you did too. And I hope you understood a bit more about our software. Have a nice day. Thank you.